Good afternoon, everyone. Welcome to this Stochastic Optimisation stream. So we've got three speakers, all from Lancaster University. Quite a mixture of different kinds of applications and methods in this session. We've got aviation applications, we've got optimal search problems, we've got dynamic allocation of resources, and the methods include stochastic integer programming, Markov decision processes, multi-armed bandits. There's only 1 hour for the session, so 20 minutes for each speaker, including questions. So since we only have quite a limited amount of time, I'm going to introduce the first speaker immediately. The first speaker is Jamie Fairbrother from Lancaster, and he's going to be talking about slot allocation at airports. So I'll stop sharing my screen. And Jamie, over to you. I'll stop my video now.
Great. Okay. Can you hear me and see my screen?
Yeah.
Great. Okay. Well, I'll begin then. So yeah, thank you everyone for attending my talk. Today I'm going to be talking about stochastic optimization model in the area of scheduling at congested airports. So let's get started. Oh, and I should add, this is a joint piece of work that I've worked on with the chair, Rob Schoen. Okay, so let's begin with some background material. So as you know, around the world, demand to use airports often exceeds the available capacity. Airports are a particularly important bottleneck in the air transport system, and as a consequence of this, delays at airports can have reverberations on the whole air network. So it's really important that we reduce delays at airports as far as we can. So how do we cope with this lack of capacity? Well, the obvious solution is just to expand the airport. However, this might not always be possible in the short to medium term. Those of you who are from the UK are probably very much aware of the situation with Heathrow Airport, for example. But it also might be impossible because of physical constraints at the airport. So generally, we have to manage congestion through improved demand management, that is scheduling, but also improved capacity management. So by which I mean really the operational logistics, such as runway sequencing and aircraft ground routing, which can have a big effect on the throughput. In this talk, we're going to be mainly focusing on the demand management. So I'll briefly explain how this works. Demand is managed through the allocation of takeoff and landing slots to airlines. And a slot is simply just a short time interval during which an aircraft can land or take off. And at the strategic scheduling level, these slots typically are about 5 to 10 minutes, sometimes 15. And we usually assign several aircraft to each of these slots, depending on the airport's capacity. And yeah, the focus on this talk will be how do we actually allocate these slots to the airlines. So an important consideration when constructing a schedule, and the feature I'm really going to be focusing on today, is the queuing performance that schedule yields. So what do we mean by queuing here? This means different things for arriving and departing aircraft. For an arriving aircraft, this might mean the aircraft has to circle the airport in the air in a holding stack, which is something we particularly want to avoid wasting fuel and avoid increasing any unnecessary risk. For departing aircraft, it usually just means the aircraft is waiting on the ground at the gate, perhaps. So we want to avoid delays, particularly delays in the air. So the current practice is used to construct schedules. We firstly, before any scheduling takes place at all, an analysis of the airport predetermines a capacity, the airport's capacity, in terms of the number of runway movements we can have over given periods of time, the available apron stands, and the terminal capacity in terms of numbers of passengers an airport can cope with. Usually it is the runway constraints that are the main constraining factor though. Once we have these capacity limits, a schedule is constructed which doesn't exceed these limits. And many deterministic optimization models have been proposed already for this purpose. However, we think that this perhaps isn't the most effective way of controlling queuing. Queuing, in particular, such an approach could easily be too conservative. That is, the restrictions are too high, and we don't use all the airport's available capacity, or it could be too lax, in which case we schedule too much, which leads to queuing. So instead, what we do is we're going to propose a new two-stage stochastic programming model for slot allocation, which explicitly incorporates queuing into the model. Okay, so now I'm going to talk a bit more about scheduling and queuing. So due to the capacity limits that I've already mentioned, some airlines will not be able to receive their preferred slots. Apologies for the typo on the slide there. We call the difference between the preferred and arrival slots the scheduled displacement. And typically the aim of a slot allocation model, whether deterministic or stochastic, will be to minimize the scheduled displacement in some way. And it's important to do this because airlines, passenger demand for flights are quite sensitive to time, but there are also issues with airline logistics as well. For example, an airline will need compatible slots for its origin and destination airports. Okay, so queuing, generally a very non-stationary schedule, that is a schedule with peaks and troughs. It tends to produce longer queues. And so when we're from a queuing perspective, when we're constructing a schedule, we prefer the schedule to be flatter. However, demand is naturally peaked. And so this means that there is implicitly a trade-off. There is a trade-off between queuing delays and schedule displacement. Okay, so how can we control queues? So some work has been done on this, and they've usually used a simple scheme like this. So the scheduling has been decoupled from the queuing. So it's a simple iterative scheme. We construct a schedule based on current limits. The queuing performance is then evaluated through some sort of simulation. If the queues are small enough, then we stop and output our schedule. If not, we tighten the capacity constraints and construct a new schedule. But yeah, we argue that this approach will probably produce too cautious a schedule, and so which is why we develop a model which directly incorporates queuing into it. So on this slide, I have the figure of the queuing model that we incorporate into our stochastic programming model. So what happens is we have an aircraft arriving at the airport. It arrives at the airport at its scheduled time plus some random delay. It then enters an arrivals queue. We model the arrival queue, the service time of this queue with an Erlang distribution for mainly reasons of tractability. Once the aircraft's exited the queue, it joins the departure queue, either at its scheduled departure time or if it's delayed, whenever the aircraft is ready. And it then enters a departure queue, which also has Erlang service times, and finally exits the system. So, however, we can't, for a stochastic linear program, we can't incorporate a continuous queuing model. And so what we have to do is we have to discretize this model, and we discretize the queuing model into short periods, which we call operational intervals. And our model will record the length of the queue at the end of each of these intervals. In particular, the approximation that we use to calculate the length of the queues is as follows. The queue length of a new period is the queue length of the previous period plus the number of entries into the queue minus the number of service completions, or 0 if this term goes negative. And this approximation is equivalent to assuming that aircrafts will only ever enter the queue at the beginning of our operational periods. And so in general, this approximation will tend to underestimate the queue length, but it gets better during busy periods. And as this interval length, the length of operational intervals gets smaller. And I illustrate this in the figures below. We have on the orange lines, we have an exact queuing process. On the blue lines, a discretized process. On the left-hand side, we're using discretization of 2 minutes. You can see it roughly follows the shape, but it misses out the details, whereas a discretization, a much finer discretization of half a minute, almost follows the process exactly. Okay, so I'll present the model now. So as I said, it's a 2-stage stochastic programming model in which the first stage of this model consists of constructing the schedule, and the second stage consists of evaluating the queue lengths given the random delays and the random queuing service times. This is quite a complicated model, so we have to make some simplifying assumptions. In particular, we assume we're allocating slots for a single day rather than a whole season, and we're mainly for simplicity of exposition, we're disregarding some extra complications like priority classes and apron terminal constraints. So I have 5 minutes left, so I'm going to I'll probably go over this quite briefly. The inputs to our model are a set of arrival and departure requests with their preferred times. We also have minimum turnaround times between arrival departure pairs. The first stage of the model consists of simple binary variables indicating whether a particular request is allocated slot or not. And these are subject to the constraints that we assign every request a slot, and also turnaround constraints. In the second stage, the scenarios, that is the randomness, consists of arrival delays from the scheduled time, and also random service times for the Erlang service distribution. And the output then looks like this. For each scenario, we have a queuing profile, across the day. So the question is now, how do we how do we actually control this queuing delay? How do we, in our objective, how do we flatten these peaks? So one idea would simply to be just use the expected queue lengths. However, we argue that this isn't the most effective way of controlling peaks. So instead, we propose to use a risk measure called the conditional value of risk. This can be thought of as the average outcome in the beta % worst cases. Crucially, it's tractable in the context of optimization. And this is our overall model. So we minimize schedule displacement subject to the first and second stage constraints I've mentioned. And we have CVAR constraints, separate CVAR constraints for arrivals and departure queues. So I'm running out of time, so I might just, I might have to skip over some of these numerical tests, unfortunately. But essentially we randomly simulated some requests with sensible turnaround times, etc. And we implemented the model in JUMP for Julia and solved it using Garobi. And we do this varying the CVAR constraint. And what we observe is, as expected, as we tighten these constraints, we do indeed get flatter schedules with better queuing performance. So to conclude, yeah, we've proposed a new stochastic programming model for slot allocation. The queuing model incorporates, unlike previous approaches, uncertain arrivals, uncertainty in service times, and a coupling of arrival and departure movements, often treated independently. A numerical tests of the model indeed demonstrate that they do mitigate against the worst case. So we still got, this is a work in progress. We still got to test the model a lot more. And it's quite a difficult model, so we'd like to improve the solution efficiency as well. And that's it. Yeah, if there are any questions, perhaps I don't know.
Okay, thank you, Jamie. You finished in good time there.
Oh, good, okay.
We do have one question, actually an observation, okay. Which is that arrivals could be early if the jet stream is helpful, and can be maybe up to 1 hour early. So does your model allow for early arrival times, and how does that differ from the case of departures?
Yes, yeah. So although I use the word delay, this delay can take a negative value. So that's absolutely fine. Flights can arrive early, and this delay can also depend on the flight as well. So we could take into account a long distance flight, which might be very early, for example, in principle.
Good, okay. So you're obviously talking about slot allocation. You can think about trying to decide the schedule for a single day or for a whole season. How realistic is it, do you think, to imagine that we might be able to do this for a whole scheduling season?
I think that would potentially be very difficult. I mean, it's hoped that we can maybe use a heuristic to do this, but I can't, to be honest, I kind of see this as more of a, it could equally be used as a scheduling intervention, I guess, on the day if we have reduced capacity. But yeah, I mean, this is something we need to think about as well, I guess.
Yeah, so you mean making changes to an existing schedule?
Yeah. In the case of bad weather, for example.
Okay, well, good. Let's move on to our next presentation then. If you can, thank you very much, Jamie, if you can turn your screen off. So the next presenter is also from Lancaster, Jake Clarkson. Over to you, Jake.
Thanks, Rob. So I should just share my screen. Okay, right. So good afternoon, everyone. I'm Jake Clarkson. I'm a postdoc at Lancaster University, and I'm going to talk about some work that I did during my PhD with my supervisors, Kevin Glazebrook from Lancaster and Kyle Lynn from the Naval Postgraduate School in California. So we optimize the way that we search for an object so we can find it in the quickest possible time. So why is this important? Well, in real life, there may be huge costs involved in conducting a search, and there may be severe consequences if a search fails. For example, in marine salvage, it could be very costly to send a diver down to the bottom of the ocean, and in search and rescue, there are human lives at stake. So we've got ample motivation. So we look at a problem where a searcher has a choice of two search speeds, fast and slow. But before I introduce that two-speed model, it's necessary to talk about the same model, but with a single speed, and discuss its simple optimal solution. So to introduce the model, what have we got? We've got a sole object that doesn't move, which is hidden in one of n discrete boxes. So just imagine you've got n boxes on the table in front of you. There's an object hidden in one of them. You don't know which box the object is hidden in, but you want to find the object as soon as possible by making successive searches of all the boxes. So at the bottom, I've got 3 boxes. I'm going to run with this 3-box example throughout the rest of the talk. Now, for each box, we've got 3 pieces of information. So 3 bits of notation to remember P, Q, and T, and they're all known to the searcher before the search starts. So first, each box I has got PI, and this is just the probability with which the searcher believes the object is in that box at the start of the search. So for example, for box 1, P1 is equal to 0.5. So this just means before the search starts, the searcher thinks the object is in box 1 with probability 0.5. And we can see that these probabilities sum up to 1 over all 3 boxes, so there's no chance that the object can lie elsewhere. Now, we're also going to allow for the concept of the boxes to be messy. So we may make a search of the box where the object is, but not find it. We may have to revisit it to find it. So we're going to say QI is going to be the probability that the object is found on one search of box I if the object is located there. So for example, for box 1, Q1 is equal to 0.4. So if the object is in box 1 and we search box 1, we find it with probability 0.4. If the object isn't in box 1 and we search box 1, then we've got no chance of finding it. And finally, for each box, TI is just the time cost that it takes to search that box. Now, throughout the search, the Q's and the T's are going to remain constant. So no matter how many times I've searched box 1 in the past, if I search it again, Q1 is equal to 0.4 and T1 is equal to 5. It takes time 5 to search it. The P's, on the other hand, represent our belief about where the object is, and this can change as the search goes on. So, for example, if I search box 2 and don't find the object, my belief that the object is in box 2 is going to decrease, and my belief that the object is in boxes 1 and 3 is going to increase. And we do this updating using Bayes' theorem, and I'll explain that exactly how that process works in a couple of slides' time. First, just some rules about the search. So we're not allowed to make any partial searches. We can't make half a search of box 1 or half of a search of box 2 or anything like that, only full searches. And we're also going to assume that each search fails. So we're going to constantly ask ourselves the question, where would we search next if we hadn't yet found the object? So what this means is that a search policy just becomes an ordered infinite list of boxes for the searcher to search. So with this example search policy here, the first search the searcher makes is of box 2. If that search fails, the second search is of box 3. And if both the first 2 searches fail, the third search is of box 2, and so on and so on. And we want to just find the search policy that finds the object as soon as possible in expectation. And it turns out this is quite easy to do. And the simple optimal search policy was first discovered in 1962. And all it does is for each box, it calculates its Gittins detection probability Q divided by its search time T, multiplied by our current belief that the object is in that box, which is we represent by P dash. So then all we do is we calculate the indices for each box, pick the largest index and search that box. That is the optimal box to search. So for my little example here at the bottom, I've calculated the Gittins index for each of the boxes. Box 2 is the largest, so the optimal thing to do is to search box 2. Now the Gittins index for a box summarizes the value there is in searching that box, and P times Q divided by T is quite a natural choice, because if we think about what it is that attracts us to searching a box, it's a large chance of the object being there, so a large P, a large chance of finding the object if it is there, so a large Q, and only a small time cost, so a small t. So now I'll just quickly show you how this policy works in practice. So we've already uncovered that the optimal first box to search is box 2. So let's put that into the optimal search policy. Now we're going to make that search for box 2. We assume that it fails, so our belief that the object is in box 2 is going to go down. So our new belief that the object is in box 2, which is P-2, is proportional to our old belief, P2, multiplied by the probability of the search for box 2 failing, which is just 1 minus its detection probability. And this is just Bayes' theorem. Posterior is proportional to prior multiplied by likelihood. Now, we haven't seen any data for boxes 1 and 2, so their posteriors are just proportional to their priors. And now what we do is we could normalize these posterior probabilities, but all this would do is involve dividing each of the indices by the same value. And since we're only bothered about which is the largest index, we're not actually bothered about the value of the indexes themselves, we don't have to do this step. We can already see the next optimal box to search. And see, we've actually got a tie between the indices for boxes 1 and 3 for the largest, and a Gittins index can split a tie any way that it wants. So it's both optimal to search box 1 next and box 3. So let's just choose box 1. And then we will just carry on, assume that this search of box 1 fails and carry on, and we can fill up our optimal search policy like that. So the key takeaways from the single speed optimal policy are that it has a very simple form and it's very easy to implement. So now our extension gives the searcher 2 ways to search each box, a fast speed and a slow speed. So when deciding which speed to use, there's a trade-off for the searcher between the speed of the search and the accuracy of the search. The fast search is quicker, but there's more chance of missing the object using a fast search if it is there. Our motivation for this is due to advanced technology, meaning that drones and robots are often used for searches, and these drones and robots will have multiple search settings. And also we're motivated by some search problems having several choices of search agents. So for example, a bomb squad may have a choice between going in a censored vehicle, which should be the fast search, or going on foot with sniffer dogs, which should be the slow search. The vehicle travel is quicker, so it's got a smaller search time, but it's also got a smaller detection probability. It's more likely to miss a bomb. So now just to formalize this, each box has got 2 detection probabilities and 2 search times, with the fast version lower than its slow counterpart. As you can see now, for the example at the bottom, each box has got a fast detection probability and search time in red, and a blue detection probability and search time in blue. And I'll run with the colors red and blue for fast and slow throughout. So now each time the searcher has to make a decision, they not only have to decide a box to search, but also a speed at which to search it. So this means that a search policy now becomes an infinite list of 2 tuples. Like, for example, in this one here, the searcher first makes a fast search of box 3. If that search fails, their second search is a slow search of box 2, and so on and so on. So a first question that we could ask ourselves is, well, can we extend the simple optimal policy for the single speed problem to the 2-speed problem and give each box 2 indices, a fast index formed by its fast detection probability and search time, and a slow index formed by its slow detection probability and search time. Then we've got 2 indices for each box, 2n, where n is the number of boxes, indices in total. So could we just look at the largest of these 2n indices and search the corresponding box at the corresponding speed? Is this the optimal thing to do? So in our example here with 3 boxes, we've got 6 indices here at the bottom. The largest is the fast index of box 3. So is the optimal thing to do a fast search of box 3? Well, one thing to notice about this is that for any box I, Q and T for both fast and slow are fixed. So what this means is that one index, either the fast or the slow, is always going to be larger than the other, no matter what this value of P-I is. So this means in this candidate policy, we're only ever going to search a box at one of its speeds, the speed with the larger value of Q over T. So when we actually implement this candidate policy, we can throw one of the speeds for each box away. So in this example, for box 1, the slow index is greater than the fast index. This will be the case no matter what P1 changes to throughout the process, so we can throw fast away. And similarly, we can throw slow away for box 2, and we can also throw slow away to box 3. So if all this were true, then any 2-speed extension would just reduce to a single speed problem. But think about what would happen if for some box the slow ratio is equal to the fast ratio. Then by the above logic, it would be equally optimal to search box I fast and slow whenever we want to search it, even though a slow search of box I involves a lot more of a time investment than a fast search does. So this may be the first sign that this logic above it isn't, the 2-speed extension isn't quite as simple as this. Now, there is a more concrete way in which we can use Gittins indices in our 2-speed extension. So for each box, I'm going to fix a sequence of speeds, AI, and this is going to determine how I make successive searches of box I. So, for example, if I fix AI to this sequence here, the first time that I search box I has to be slow. The second time I search box I has to be fast. The third time has to be fast as well, and so on and so on. So what this does is this takes the choice of speed away from the searcher. So now all the searcher has to do is make a choice of box, exactly like a single speed problem. And it turns out in a world where we fix these speed sequences A1 to AN for each box, a Gittins index is optimal. And which index we look at for box I, its fast index or its slow index, just depends on the next speed in its speed sequence. Therefore, our challenge in the 2-speed extension is just reduced to finding the optimal speed sequence A star I for each box. Because once we have these optimal speed sequences, we can just throw a Gittins index policy at the problem and it is solved. And we've got a few some theorems which determine this optimal speed sequence for certain boxes. So first, we've got a slow theorem, and what this says is that for some box, if the ratio of slow detection probability over slow search time is greater than or equal to the same ratio for fast, that box is always optimally searched using its slow speed, no matter the other boxes in the problem. So its optimal speed sequence is just full of S's. So this shows that what we were pondering before, when the slow ratio is equal to the fast ratio, for such a box, it's always optimal to search it at its slow speed. Now we think, well, can we flip this inequality here and say the same thing for fast? So when the inequality is reversed, fast is always optimal. And we can't quite do this, so we need to multiply this QIF by 1 minus QIS. So if you keep your eye on this equation here, you can flip it, multiply by 1 minus QIS, and for such boxes, it's always optimal to search them fast. And one brief thing to mention is that these are sufficient conditions for optimality. So there could be other boxes which don't satisfy this inequality, which are optimally always searched at their fast speed. So we can use our theorems to partition all boxes into 3 subsets. So if we let S be the set of boxes which satisfy the slow theorem, so a slow search is optimal, F be the set of boxes which satisfy the fast theorem, so a fast search is optimal, and let H be all other boxes. To just give you an idea of what these 3 sets look like, I'm going to fix all parameters apart from TS, the slow search time, then increase TS, which makes the slow search worse. We can see that this unknown set H sits in the middle of S and F, as you would expect, and also this unknown set H can be quite large. So we know how to search boxes in S, always slow. We know how to search boxes in F, always fast. We're going to turn to heuristic policies to search, to determine how to search boxes in this grey area H. The simplest type of heuristic policy is a single speed heuristic policy, which just takes a box in H and either always searches it slow or always searches it fast. And we've seen one of these already. If you recall our first sort of thought about looking at a fast index and a slow index for each box and looking at the largest overall 2n indices, which just reduced to searching a box always at the larger at one speed, depending on which was the larger of these 2 ratios, Q over T. Well, this was a single speed policy. And by the slow theorem, when for any box for which the Q over T for slow is greater than Q over T for fast, that box is in S, so it's always optimally searched slow. So for all boxes in H, this fast ratio is greater than this slow ratio. So this single speed policy, which we call the maximal index heuristic policy, takes all boxes in H and searches them fast. So basically just takes the grey area H and colours it in red. Now, one question to ask is, can we do any better than the maximal index policy with a single speed policy? And the answer to that is yes. The answer to is it always the best is no. So we'll say that the best single speed policy, we'll call that the best single speed policy. And for each box in H, we've got two options: either search it always slow or either search it always fast. So to find the best single speed policy, we've got 2 to the power mod H candidates to exhaust. Now, single speed policies are good because they're quite simple. We have to bother searching box in H at just one speed, but we do have the ability to search these boxes in H at either of their speeds, and we aren't using this. So can we take advantage of this ability? To do this, we consider the 2 different types of benefit to searching a box. So the first is the actual chance of finding the object. And for boxes in H, fast is better at this per unit time as slow, because this fast ratio, which is just its detection probability per unit time, is greater than the slow ratio. The second benefit is about learning about the object's true location after a failed search of that box in H. How quickly do we learn that the object is elsewhere? We measure this by the rate at which our posterior belief that the object is in that box H drops as we make a failed search of it. It turns out there is a region in H where slow is better than this per unit time than fast. And an example I've been going with is between 1.6 and 2, but on 2 to 4.4 and beyond, fast is better. Now, if we think about these 2 benefits, the first is about actually finding the object. Well, this is more significant when we believe the object to be in our box, so when P is higher. The second, which is about learning that the object is elsewhere, well, this is more significant when the object is elsewhere, so when P is lower. So this motivates, so on this region here, 1.6 to 2, where fast is better at benefit 1, slow is better at benefit 2, this motivates a threshold policy to search fast when P, the belief that the object is in our box, is greater than the threshold, and slow when P is lower than the threshold. And we just calculate this threshold simply by just equating the value of these 2 benefits. Above 2, because fast is better at both of these 2, we heuristically just search fast. And we call this policy our best threshold policy. This is our 2-speed heuristic. So just some numerical results. So just a quick reminder here of what all the heuristic policies are. So for 2 boxes, we took both boxes in H, so both we don't know what the optimal thing to do is. The values in this table are the mean percentage over optimal over 2,000 problems. So the first thing we can see is that all the heuristic policies are pretty close to optimal, but the best threshold policy, our 2-speed heuristic, is the best, particularly once we get into the tail, the worst performing problems. We did the same for 4 boxes, and we saw similar results, apart from this maximal index, which always searches fast, gets quite a bit worse. And we think the reason for that is when you've got more boxes, there's more uncertainty about where the object is. So this better learning ability that slow has got becomes more valuable. So just to summarize, the single speed version of our problem has a simple solution, which first solved in 1962. But when we introduce a second speed, this makes the problem more complicated. We found some theorems which show when boxes are always searched fast and when boxes are always searched slow. And by using this theory, we can come up with some reasonable single speed heuristics, which are simple. But looking into it deeper and considering the benefits of searching a box, we've come up with a 2-speed heuristic that performs very closely to optimal. And the bottom reference here is the write-up of this work, which I did with my supervisors, and the top one is the first paper that found the single speed result. So yeah, thank you very much, and I'll be happy to take any questions.
Okay, thank you very much, Jake. That was great. I don't see anything in the Q&A, but just to ask a question myself, this might be quite an obvious question to ask, but have you made any progress in looking at problems with more than 2 search modes?
We have, yeah. What we've found is that we have found some conditions for basically if we have one box. So say we've got a box with say 3 search speeds. If one of those speeds dominates the other 2, then we can, via those theorems, either by the slow theorem or the fast theorem, we can show that that mode is dominant and that you should always use that mode. What we can't show, and that we conjecture to be true, is that, say, if mode 2 is dominated by mode 1, but not by mode 3, that mode 2 shouldn't be used, because there might be some there might be a combination of modes 2 and 3 that actually then beats mode 1. So we've extended with a bit of theory, which is actually, there's a small section of this paper here that talks about that dominated theory that we did manage to prove, and also makes that conjecture. So yeah, so we've made some progress.
Okay, good. It does sound quite a bit more complicated then if you have more than 2 modes. Okay, thank you very much, Jake. I think we will move on to our final speaker, Stephen. So I'll briefly introduce Stephen. Stephen is also a story student at Lancaster, and he's going to be talking about a problem involving dynamic allocation of resources. Over to you, Stephen.
Okay, just one moment. Let's see, does this work? No. Haha. Right, can you see the presentation?
Yeah.
Hello, right, I'm Stephen, and this is my talk about dynamic allocation, subject to failure and replenishment. I'm from Lancaster. This is a PhD at Stora. It's funded by the EPSRC, so we've got to be nice to them. And one of my supervisors is from the NPS, Naval Postgraduate School, about which more anon. So first I'm going to give you an outline of this talk, so you know what's going on. I'm going to start with a description of the problem and some real-world examples of the problem. Then I'm going to give you the mathematical formulation. And the crucial aspect here is dependency. The rewards depend on on the whole of the state in quite complicated ways, which is unhelpful. Then I'm going to give you the idea of a policy framework. We can't find the optimal policy for reasonable problem sizes. It turns out the state space is just huge. But we can find certain elements of the policies which are necessary for a policy to be optimal. Then I'm going to give you some numerical results, have to do some generalizations, which we've also tried, and a look at some what we've done that is different and what we haven't done that would be different. So we're going to start with the problem. The original problem came from the Naval Postgraduate School out in Monterey, California. It's naval search. We've got a large area, generally ocean, which we need to search. We need to communicate back the results. The specific incident was using UAVs to allow a large number of searches. We're expecting something between 10 and 100. So we're not using numbers so large that we're thinking, oh, well, we'll just use approximate as continuous. And we're not using numbers so small that we can actually just formulate it and get the optimal policy exactly. So we're talking about this kind of UAV, not huge Boeing 747 types, not tiny little quadricopters. Lifespans in terms of flight times measured in terms of hours. So we've got to take into account refueling, accidents, replacement. We've got to take into account replenishment and repair. We can't just assume that we'll send them out and they'll be good forever. We're searching over a large area, so it will probably take, we might want to keep up a search for months. We have other examples. The first example I give, always because I can use a picture of a dog, is search and rescue. This one's slightly different in that we might want to search just to completion until we find the lost hiker or whatever. Additionally, we might well have heterogeneous assets. We might have search teams on foot, we might have search dogs, we might have helicopters. But again, we've got that aspect of we probably aren't just going to search, we aren't just going to be able to just send everyone searching until finished. We are going to have to take into account replenishment and failure. Another example, which has an interesting aspect, is that of monitoring forest fires, which is, of course, very relevant right now. Here, what we have is probably a trade-off between risk and reward, in that the closer we get to the front of the fire, the more accurately we could monitor it, but the greater the risk of failure from smoke and fire crashing our drones or whatever completely. A last example is of wildlife monitoring. Here, what we need to do is to surveil an area for a very long time, and we might be using quite cheap drones, so we will be expecting to fail a lot. We need to monitor it for a long time to get an accurate estimate of the number of animals. It's not always going to be as easy as monitoring elephants. So let's move on to some actual mathematics. We're going to start by saying we're not trying to find the optimal policies. The whole point is that we want to deal with cases that are too large for that. We want to find effective policies, not optimal. So we start with, as always, a Markov decision problem model. Now, I can hear some of you saying already, oh, but that's unrealistic. Oh, reality isn't memoryless. How do you explain America then? but it lets us actually get somewhere. It lets us actually formulate it. It lets us, for small cases, calculate an optimal policy to tell how well everything else is doing. So we say we've got n assets. These are our drones, our dogs, or whatever. We've got k tasks. These are places we need. These are the communications places. These are the search places. Xk is the number of assets of task k. We've got a repair process. It's labeled k+1. This might actually be more than one process, but we represent it as one, and then just say, well, maybe the repair rate depends on how many we've got. And we've got a reserve. This is actually a really important part. We don't have to send out everything. Maybe right now there's not much forest. The forest fire is quite small. We only need a few assets, so we keep the rest of them back so they're not at risk. So we've got failures. Our failures are Markovian, they're exponential. They're failing from task k at a rate mu k. We've got assets being repaired at a rate lambda of xk+1. That is, it depends on just on the number of assets we have being repaired. You'll notice I've used mu and lambda. This is deliberately reminiscent of a queue. It's kind of similar to an infinity queue in that you've got assets coming in to the sort of the tasks at a rate lambda, and then you've got them kind of going out at a rate mu k xk. Once we've prepared an asset, we can allocate it to a task, we can reserve it. Everything's exponential, everything's Markovian. I've got a helpful diagram. We start with the allocation decisions, we send to any of the k tasks. We have the failure rates coming down from that, which go to the repair process. From the repair process, we have the repairs coming out at lambda of xk+1, and they can either go to the reserve or back to the allocation. Now, given this, we need a reward function to actually make it a proper Markov decision problem. Now, this is a fairly complicated looking expression, but it's not as bad as it seems. What we're saying is that task k, that's search. Again, you might think this is actually several tasks, and we just put that into the reward function. But that's where we can get our reward from. The previous k+1 are the communications. We need to have at least one asset in each of them to get it in. Again, it might actually be more complicated than this. But for now, it's a Markov decision problem. We want the simplest formulation that still gives us difficulties, that still captures the fundamental difficulty of what we're dealing with. So we need a communications chain and then assets at the last task search. There's a slightly smaller formulation, which is weirdly almost more general. We just have two tasks. The first task is communications. We need at least C assets. The second task is search, and that's where we get our reward from. If all the failure rates for communications are the same, there's no reason to think they would be. The two are equivalent. We're going to use the second one mainly because it's smaller, and that lets us, when it comes to do numerical simulations, check more cases. So now for the policy skeleton. If you look at that reward function, there's something fairly obvious about it. We have to sort out the first bit before the second. If we haven't got C assets at the first task, we're not getting anywhere. It doesn't matter how many assets we have searching. So we put together a communications chain, then, and only then, do we worry about allocation versus reserve. If we can't do that, if we don't have enough to form a chain, we just wait until we get more assets repaired. So this is a horrible looking expression, but it's basically saying, do we have enough to form a communications chain, C, and then have one asset left over to search? If we don't, we wait. We wait for the next event. We don't know what's going to happen. If we do, then we look first at the communications chain. If X1 is equal to C, that is, we have a communications chain, we don't have to do anything. If it isn't, then we send a bunch of assets to task 1. So we form a communications chain. Then, and this is where a miracle occurs, we send some number of assets from reserve to search. That's why I call it a skeleton. We need to put some meat on the bones. So how do we decide how many we reserve? How do we decide how many we send? The simplest idea, which is surprisingly non-terrible, just send a constant fraction. You've got fraction theta of them go to search, the rest go to reserve. Obviously, there's some massive discretization going on here because we can't send 0.3 dogs out. Well, it would be rather cruel for a start. Interestingly, if we just make it half and half, it does surprisingly well across a really wide range of parameters and functions, considering how ridiculously simple it is. And it's indifferent to the problem parameters, which on the one hand, well, that's stupid, but on the other hand, it means it can't be fooled. So how do we make this better? Well, policy improvement is the standard technique on Markov decision problems. We can't then run it to completion here for computational reasons, but we can generally get away with one step, especially when you consider that we're computing the policy first and then using it. So we can afford our policies to be slightly less efficient. It's O of mod x cubed time, which is not great, but it's not absolutely terrible. A separate way of thinking about it is theta is in the interval 0, 1. We only really need to know it to a precision about 1 over n, the number of assets, because of the discretization I just mentioned. So we can theoretically search it just only n plus 1 evaluations to find the best theta. That's also O of mod x cubed time. Again, not great. We could then run one step of policy improvement on that. And the nice thing here is we've got a kind of ladder of making the policies more complicated, taking more computational time, but we would hope making them better. So here's the results. We can find the optimal policy through repeated policy improvement. We've got an O of mod x cubed time per cycle, but it's horrific in the worst case. In practice, that never happens. It rarely takes more than 10, but it could be something absolutely ridiculous, which is why we can't find the optimal policy for real things. I mentioned earlier I wanted to have 10 to 100 assets. For the cases we actually run, at most we've got 10 assets because computationally it takes so long. So we run a bunch of combinations of parameters where you think we've got the mu k, we've got the lambda, we've got the n, we've got k or c depending on the formulation, we've got the form of g of x2. So we run a whole bunch of combinations of them. We express the reward gained for each policy in each scenario as a fraction of the optimal. Because obviously, some cases are easier than others. If you only need 1 asset to form a chain, that's easier than if you need 8. And we're going to plot the quantiles to give a fairly standard looking graph, which still requires some explanation. So we've got a bunch of policies, and we've got the quantiles. An ideal policy would go straight to the top, and from the top would continue along over here. The worst policy, the one that we've got at the bottom, is just randomly allocate assets. It's actually good to see that this is bad. This problem is difficult. Sometimes you find that you've accidentally formulated a problem in such a way that any policy will do well. This isn't the case here. And then we've got going up the ladder. We've got our simplest policy, just half and half, theta equals a half. It's not great, but it's not terrible. It's 80% of the optimal, 90% of the time. Then if we find the optimal theta, that's a bit better. If we have a single step of policy improvement on theta equals a half, that's even better. And if we find the optimal theta and then run a step of policy improvement on that, we get a policy that's very, very close to optimal. And in fact, looking at the numbers exactly, 80% of the time, it is the optimal policy, despite having a much better worst case runtime and a better practical runtime. So one step of policy improvement is the key. Theta opt plus is the best, but it's also the most time consuming. We've got this nice trade-off between the computational time and effectiveness. So now that we've solved the problem, of course, in the typical mathematical fashion, we decide to make it more difficult. I mentioned earlier, we can kind of imagine we've got multiple search tasks in one, but what if we actually have multiple search tasks? There's no reason we can't. There's a whole paper in this, seriously, it's in the citations at the end, but we can start with the existing policies and so only really change what was in box 4. We start with the policy deciding whether to allocate or reserve. And then once we decided whether this asset should be allocated or reserved, if it's reserved, well, there's still only one reserve. If it's allocated, then we use something else to decide which task to allocate it to. That's something else. There's 2 things. There's Whittle indices of restless bandits. This is complicated in a whole talk of its own, but basically it's a way of using some not quite optimal, but close to optimal stuff, and very computationally simple stuff to pick the best search task at each moment. And here we've got the graphs, fairly simple. Again, one step of policy improvement makes a big difference. The performance isn't as good, but we'd expect that to be the case because we've made things more complicated. What is interesting is that the gap, the suboptimality gap, isn't much more than the sum of the 2. Like if you just had the search tasks and no communications, obviously there's a suboptimality gap. If you just had the search, the one search task, then you've got a suboptimality gap. We can put these problems together and not make them any more difficult. We still got a handle on what's going on. So we can also generalize it in another way. Airline distributions, which are always nice because they're still technically Markovian but allow a greater deal of generality. We just stick 2 phases on each task to start with. We can obviously have more. We use the total number of assets at each task for like calculating the rewards and stuff. The dynamics are still Markovian. We can still use policy improvement, and we can generalize to more phases, but we don't want to because the state space gets horrific. Again, we've got this graph is frankly too complicated, but we've got the same kind of thing. If we take into account the full 2-phase formulation, then we do even better. If we don't, we're still okay. Now for the last one, and this is the last one, and I'm aware I'm running out of time. It's non-Markovian. Now that should strike horror into everybody's hearts. We've got a generalized distribution. It could be deterministic even, it could be uniform, it could be something really weird, it could be just variable hazard rate. Now, what we can do is, obviously any distribution will have a mean. Any reasonable distribution will have a mean. We can match it to the equivalent Markovian case, because with an exponential distribution with rate mu, its mean is 1 over mu. We can use the policies from that, so we can at least give something to it for the start. But there is absolutely no way that I'm aware of, that any of my supervisors are aware of, to find the optimal policy. We cannot be sure that we're doing well. And for that reason, I don't have a graph. I've run various simulations and got various answers, but there's no way of telling, are we actually doing well? I don't have an analytic upper bound, I don't have an analytic lower bound, other than really stupid ones. So what have we actually achieved? I've given it all. The problem of optimization failure is surprisingly uncommon. I know people are going to say, well, I do that. Yes, people do. But more often what you have is you have things to do with optimization, or like the previous 2 talks, where your assets are fairly dependable. Or what you get a lot of, especially in telecommunications work, is we have a complicated system. What is the chance the whole thing fails if one of the individual things fails? Putting the 2 together makes it much harder, which is fun. We've addressed a specific real-world case. The idea of dependency came from my supervisor, Mike Atkinson, at the Naval Postgraduate School. We've got a lovely trade-off between computational practicability and effectiveness. If we want to make things more complicated, we can. And it's robust, not in the proper sense, but it's not massively sensitive to the specific assumptions in the formulation that we make. So, lastly, we've got extensions. The non-Markovian case. If anyone has an idea for a non-stupid upper or lower bound, I would love to hear it. The second thing is we might think, I mentioned restless bandits, bandit problems, you've got that degree of unknownness. We had Jake's talk where you don't know which box it's in. So you've got that kind of reinforcement learning thing of we don't know where we should be searching, we don't know where's best to search. The trouble is, the obvious way to formulate that is you've got kind of rewards arriving as a Poisson process. If you do that, it turns out you end up with a negative binomial distribution, which has a very high variance, and it's very hard to do learning when your variance is several times your mean. One thing I mentioned to do with search and rescue is heterogeneous assets. That makes the state space much worse, but it might be very relevant to certain things. So I've got 2 citations. The first is a rather good paper about this kind of problem, multiple UAVs, persistent surveillance. The second one is me and my supervisors, and it's a description of the stuff to do with Whittle indices and restless bandits. So thank you very much for coming to this talk. Thank you very much for sitting through the whole hour of this thing. Are there any questions? I can't see.
Thank you, Stephen. I think you finished right on time there. So you were talking right at the end about maybe using an Erlang distribution to approximate a non-Markovian distribution. Do you have any information from the NPS or anywhere else about what kinds of distributions would be realistic for the failure or replenishment?
Yes, which is why we went into non-Markovian. The 2 kind of things, well, 3. The first thing you might say that's stupid but effective is just deterministic. This drone lasts 8 hours exactly. This one lasts 6 hours exactly. That's not right, that's not true, but at least it's clear. This causes all sorts of really weird problems. And so weirdly, randomness makes things easier. Stochastic optimization is sometimes easier than deterministic optimization because you can't control things to the same extent. Second, you have your kind of increasing hazard rate or bathtub distribution, where you start with a high hazard rate, takeoff is always dangerous, and then it goes along with a fairly constant chance of maybe being shot down by the enemy or attacked by a pigeon or something. And then it goes up at the end, which represents it running out of fuel. The third one is just a simple kind of uniform, which is basically a bit more useful than deterministic. Like, it will last between half an hour and an hour and a half.
Great. A question has just popped up. For the non-Markovian case, have you considered general Cox or specialized Cox distributions?
I honestly haven't considered too many the answer to that is no. I haven't considered too many distributions for it because I'm still wondering. Because essentially the problem, while the problem is unsolvable, it doesn't really matter much what kind of distributions we're using.
Yeah, of course, because we can't work out what is optimal. And have you got anything to say about stochastic frontier analysis? Another question has popped up.
Not particularly. As I said, I've been approaching this very much from a what do we know we can do approach. We know we can do MDPs. We know we can do Erlang distributions. So I've been trying to work from that up, if that's any use. So there's a lot of things we could have considered that we haven't because it's difficult enough to get the basics.
Of course, yeah. Because you've got all kinds of problems just with the size of the problem and the dimensionality to begin with. Okay, well, we better wrap it up now. Thank you, Stephen, and thank you to all our presenters. We hope you enjoyed the session and please enjoy the rest of the conference. Good to see you. Thank you for your questions. Thanks for attending again, and goodbye for now.